All right, let's start some exercises on modules. Now, when I first started doing this exercise, I was getting really kind of confused because of all the notation that's sort of hidden in this section, particularly because Jacobson doesn't actually give a name to the function that you pair with your abelian group in defining a module. And I, I maybe it's just because I haven't done a bunch of exercises with modules in a while, and maybe it's just like rusty, or I don't like the um, just the hidden like this suppressing a lot of notation. But I actually ended up going through and like writing out, like giving names to all the functions and writing things out more explicitly, and it make a lot more sense to me. So hopefully they'll be helpful for you watching this video, especially if you're not comfortable with modules yet or haven't worked with them a ton. So let's get to it. So since, what do we know? We are given that M is a left R module. We know that M is an abelian group. And we have some map, phi we'll call it, from R cross M to M, which satisfies, I'll just say, the module properties. And those are just the four properties that are stated in the textbook just before the definition of a module. And I'll go through them explicitly when we actually verify that this thing that we're going to define is also a module. So since eta S2R is a homomorphism, we have a well-defined map, we'll call it psi, from S cross M to M, given by, we're going to write psi of A comma X. So A is the first entry is the element of S, and the second entry is the element of M. And this is going to be precisely, now we're going to take phi of eta A and X. So let's verify that we understand what's going on here. So we take, phi takes in an element of S and an element of X. Now, and it will give us an element of M. And so it's going to be determined by this. And that matches because phi takes in an element of R cross M and gives us an element of M. So these two functions give us elements in the same space. And let's make sure that these entries make out. So phi takes elements of R cross M. This first thing is eta of A. Eta maps S into R, and so this is eta evaluated at an element of S, and so it will be an element of R, and so this will be fine. And then X, of course, is an M, and so we're good. So M is an abelian group, and psi is a well-defined map, and so all we need to do is so to prove that M is a left S module, we must confirm that psi satisfies the module properties. Maybe we could call it the module map properties or whatever. It's not referred to by anything special. Jacobson just calls it properties 1 through 4 because he labels them. Okay, so first, let's see here. So we're going to let A and B be elements of S, and X and Y elements of M. Then, and we're just going to do a bunch of calculations here. Psi of A comma X plus Y. What is this? This is, well, literally phi of eta A comma X plus Y. But one of in fact, the same module property which we are trying to verify right now, but for phi, tells us that this is equal to phi of eta A comma X plus phi of eta A comma Y. But this is precisely, if we write this in terms of psi, this is psi AX plus psi AY. So that's precisely the first of the properties, is that if you have addition in that second entry, then you can bring it outside. So we have this equation. Now I'm just going to put a comma and keep writing, even though this is like really hard to read. Hopefully the fact that I'm writing it out as I'm saying it makes it a lot easier to kind of understand. So psi of A plus B comma X. Now we want to bring the addition outside again. So let's see here. This is psi of eta A plus B X. But we know that eta is a homomorphism, and so we can bring this addition outside. And now we can use the addition, one of the properties of phi being a module, because phi is a module, we can use the module properties, and we can bring this out to make it phi of eta A X plus phi of eta B X. But this is precisely C of AX, psi, whatever, plus C of BX. So there we go. That was the next one. Psi of A plus B, you can bring that outside. So you can bring out addition whether it's in the first entry or in the second entry. So that's that. The next one is we want to bring out multiplication in the first entry. So we have psi of AB and X is phi of eta AB X. And again, eta here is it's a homomorphism of a ring S into R, and so I'm pretty sure it's understood that eta is a ring homomorphism, meaning that not only can we bring out addition, but we can not only does it go through addition, it goes through multiplication as well, and so we get this. So let's see here, phi of eta A eta BX, right? And so then this is, and then we use the property of modules, and this one I didn't quite see what was going on until I actually wrote it out. But the way multiplication works is it doesn't quite factor out. What it turns into is it turns into phi of eta A eta B comma X becomes phi of eta A comma and then phi of eta B X. Because what it literally says is, let's see here, AB acting on X is equal to A acting on BX. And whenever you write AX, this is by definition phi of A comma X. And so here we have this is there's just one phi on the left here, because this would be precisely phi of AB comma X. But on the right here we have phi of A with the element BX. Now, does that make sense? It does make sense, because phi is a map from R across M to M. So this being bx being an element in the image of phi is an element of M, and that's precisely the type of thing we need the second entry of phi to be in, and so it makes sense. And you just put in, this is phi of bx here. Okay, so that's one reason that I think that writing out the actual names is helpful, is the names of the functions, that is helpful, is because it helps you see what's really going on here. Because it's easy to think like, oh, this is just associativity, that's very straightforward. No, there's more going on here. So, anyways, after that whole spiel, we have this, and then we just kind of convert it back into psi language. And so we have phi of eta a, comma, and then this becomes psi of b, comma, x. And now we do it again. We have psi of a, comma, psi of b, x. So am I going to fit everything on here? I think I might. And lastly, psi of, and now I'm going to label the ones. This is a little pedantic, but I find it helpful. So this is 1x equals 1 is what we're trying to prove. No, 1x equals x is what we have to prove. And so psi of 1s, because this is an element 1 of s, and comma x is equal to phi of eta of 1s, comma x. But this is precisely phi of eta is a homomorphism, so it sends 1 to the element 1. So it sends 1s to 1m, right? Where is eta? Where did I write eta? Eta, yes. No, it's a 1r. Phi of 1r, comma x. And this, because we already know that phi satisfies the module map properties, this is equal to x. So, hence, psi makes M a left S module. And that's, of course, not like a standard way of saying it. I think the standard way is probably just the way that Jacobson says it, like M is a left S module with this map, but whatever, I just decided to make it like this. So anyways, there we go. I hope that this is that this helps kind of make it clear what exactly is all going on here, because it seems like modules aren't really difficult. It's just stuff that you've already learned before, but you're doing a whole bunch of different things at the same time, and it's important to keep them straight. And so I hope this helps you keep everything straight in your head and make it clear exactly what all is going on. So anyways, there we go. We are done with this proof.